All right, class. Today we're going to we're in chapter 17. We've completed buffers and acid-base titrations, and now we're going to focus on solubility product. So, what we're looking at today is when you add, say, silver nitrate to sodium chloride solutions. Like you have a silver nitrate solution and a sodium chloride solution, and you pour those two solutions together, a precipitate forms called silver chloride. And then you have the spectator ions, the sodium ion and the nitrate ion are left over. So back in chapter 4 in Chem 170, you should have talked about solubility rules and how to write ionic and net ionic equations. So it's been a while since you've learned the solubility rules or have written ionic or net ionic equations, I would recommend you go back to chapter 4 and read that section before completing this section of chapter 17. Because that's going to be a requirement here. An understanding of solubility rules and ionic and net ionic equations are going to be a requirement in order to understand solubility product. So, solubility product is it's an equilibrium constant. So we've talked about different equilibrium constants in this class up to this point. So let's just kind of point some of those out. Look at our journey from the beginning of chapter 16 till or 15 until now. And so we have spent time on talking about equilibrium constants. And the type of equilibrium constants we have done so far in this class is we talked about Kc, which is equilibrium constant at concentration. We've talked about Kp, equilibrium constant at pressure. We've talked about Kw, the ion product constant of water. We've talked about Ka, the acidity constant. And we've talked about Kb, the basicity constant. And now we're going to talk about KSP, called the solubility product constant, KSP. So the solubility product constant allows us to quantitatively predict how much of a given ionic compound will dissolve in water. So the solubility product allows us to predict how much ionic compound will dissolve in water. So again, I can't stress enough, you need to go back to chapter 4 and look at the solubility rules and memorize those if you didn't in Chem 170. Especially, I would memorize the first part of the table, like what is soluble, and then assume everything else is not soluble. So you don't have to memorize the whole table, you can just memorize what is soluble. So if you remember this, I mean, it was like all group 1A salts are water soluble, or group 1. Anything that contains the nitrate ion is water soluble. Anything that contains the ammonium ion is water soluble. Anything that contains the acetate ion is water soluble. And then most of your chlorides and bromides and things like this are water soluble, but there were some exceptions. And those included mercury. If this is attached to a mercury ion or a lead ion or a mercury lead, or there's another one here, I'm just kind of drawing a blank right this second, but that's what you need to go back and look at. Okay, and then there's the same thing for sulfates. Most of those are water soluble except for the mercury, the lead, and the barium, calcium sulfate and barium sulfate, I believe it is. So just go back and look at those. Just memorize those. There's no getting around that. You have to be able to do that. All right, so we're going to write the, first of all, we have to have a balanced chemical equation. So here we have silver chloride, which is a solid, and it dissolves in water. And when it dissolves in water, it dissociates into the silver ion and the chloride ion. Again, notice the double-headed arrow, so we can establish an equilibrium here. So what we're looking at a beaker, and in this beaker, you have mostly water, right? And then you have a pile of silver chloride, solid. So what's going on at any given time, some of the silver chloride is dissolving into silver ions, or dissociating, if you want to get more technical, dissociating into silver ions and chloride ions. And some of these ions are reverting back to the solid form. So that's an equilibrium between the solid silver chloride dissolving into these two ions. Now, as long as there's some silver chloride present, that concentration does not change appreciably through the course of the reaction, so its concentration is actually integrated into the solubility product constant. It's a constant. And we know that pure solids and pure liquids are integrated into the equilibrium constant itself, in this case, solubility product constant. And then it's products over reactants, so here's our products. And these are both aqueous, and that's why you see them in the expression here. So here's the thing to remember. The smaller the solubility product, the less soluble the compound is. So just like we said, for K, the larger K is, the more the reaction goes in the forward direction. And the smaller K is, the more it's likely it stays as the reactants and does not progress to the products. So same thing here. If you have a large solubility product, that means most of this substance does dissolve. And if it's a really small solubility product, it says most of it stays in the solid form and does not dissociate into the two ions. All right, so we've got some technical terms here. We have molar solubility, and then we just have solubility. So it has a very specific meaning. Molar solubility is how many moles of solute, the substance present in the lesser amount, in a liter of saturated solution. So it'll have units of moles per liter. So I would like to know how many moles of silver chloride dissolves in a liter of solution at a particular temperature. So this is temperature dependent, at a particular temperature. Now, outside of chemistry, the most important solubility is just solubility, and it's in grams per liter. And the advantage of this is you don't have to know the molar mass of the substance. So you just weigh out how many grams, and you determine how many grams is soluble and how many grams is left piled in the bottom of the beaker. So this is more important outside, but you need to know both solubility and molar solubility. Now, what I find students make a mistake here is that when I write the KSP, the solubility product for silver chloride is silver ions and chloride ions, this is the solubility. This is the molar solubility because it's in moles per liter. So because we're using brackets here, we are determining molar solubility. Molar solubility is not the same thing as solubility product. Those are two different things. When you multiply the solubilities here at equilibrium, then you will get the solubility product, if these are equilibrium concentrations, the silver and the chloride. So don't get confused between solubility product and molar solubility. Those are two separate things. And generally what we're interested in solubility product to see what extent the reaction goes in the forward direction. That means that it dissolves. But in the end, I'm really interested in molar solubility. I want to know how much silver ion is in the solution. I want to know how much chloride ion is in the solution. And again, temperature, these are temperature dependent. You know solubility is temperature dependent. You know more sugar will dissolve in hot tea versus cold tea. So it is temperature dependent. Although there are substances that actually decrease as temperature goes up. So I think they show those in chapter 4. But there are some things that don't really change appreciably, or they actually decrease in solubility as the temperature goes up. All right, next slide. So it says to calculate molar solubility from the KSP, the solubility product, here's the procedure. You got to construct an ice table. You have to fill in what you know and figure out what you don't know. So again, ice table, ice table, ice table. 15, chapter 16, chapter 17. If you're struggling with ice tables, that means you need to go back to chapter 15 and do some of these. So let's look at let's look at an equation here. So we have the solubility product of silver bromide is 7.7 times 10 to the negative 13th. Notice with these solubility products for things that are insoluble in water, they don't dissolve very appreciably. So what I will tell you to do is right off the bat, just write the reaction up here. It's silver bromide solid, and that's going to be in equilibrium with the silver ion aqueous and the bromide ion aqueous. So start with a balanced chemical equation. At equilibrium, so let's look at our ice table. Since this, as long as silver bromide is present, the concentration does not change appreciably. And what I mean by that is, again, if I have a beaker here and it's mostly water, and then I have some silver bromide, it doesn't matter whether I got this much silver bromide or this much silver bromide, the concentration of the silver bromide is the same because the volume has changed and so has the mass. So that's why you see blanks here for silver bromide. That's why you don't see it in the solubility product expression. You see KSP is equal to the silver ion concentration times the bromide ion concentration. So what we know is when this dissolves in water, we're going to get S amount of the silver. Normally we would say this is plus X, right? And we'd say this is plus X. Because for every one of these that's formed, one of these has to be formed. But because we're dealing with solubility, they use the variable S here. So when we add up the initial, the change, here's our equilibrium values. We get an S and we get an S here. We're going to plug those into the expression. We're going to plug in the solubility product, which is given in a table, and we're going to solve for S. So let's do that. So what you're going to have is S squared equals KSP, and you're going to take the square root of both sides. This is a simple problem. All right, easy to do. The only problem I see with students, if you don't write the initial reaction down, maybe you get the solubility expression, product expression incorrect. But after that, it gets to be pretty easy. I mean, that's just from solubility product. You don't memorize that. That's given in the problem or given in a table. All right. So how much silver ion dissolved? 8.8 times 10 to the negative 7th molar. How much chloride ion dissolved? 8.8 times 10 to the negative 7th molar. So that tells us because the relationship between silver bromide and silver ion is 1-to-1, we now know how much silver bromide dissolved. Because the relationship is 1-to-1, you know that this is the amount of silver bromide that dissolved in the water. So then if somebody asks you for the solubility, which is what most people want outside of chemistry, if I have the molar mass of the silver bromide, 1 mole of silver bromide weighs 187.8. You can calculate that out yourself. And so if I multiply this out, I'll get grams per liter. So this is how much silver bromide will dissolve in 1 liter of solution at 25 degrees Celsius. So you're saying, okay, what happens when I have exactly 1.7 times 10 to the negative fourth grams of silver bromide per liter solution? Well, the solution actually looks like this. It's clear, it's colorless. You've reached the saturation points, what you've done. If I add one more crystal, of silver bromide, it's not going to dissolve. It's going to sink down here, and then if it's heavy enough, and then once it's down here, some of it will dissolve, and then some of it will revert back to the solid. So anything that exceeds this amount of grams in a liter solution is going to precipitate out. Now, if you dissolve more sodium bromide than 1.7 times 10 to the negative fourth, let's say I dissolved 1.9 times 10 to the negative fourth, so I dissolved more than this number here. If it stays dissolved in solution, we call it a supersaturated solution. So if you dissolve more than what the solubility is in the solution, then you have a supersaturated solution. But generally what happens is if you add more than this amount into this solution, it's just going to precipitate out of the solution. So keep that in mind. Again, if this seems kind of foreign to you, you've got to go back and read chapter 4 to get a fix on that. All right, so let's look at our first problem here. This is calculate the solubility, not the molar solubility, the solubility of copper 2 hydroxide in grams per liter. So they're giving you an indicator. They say solubility, and then they should tell you what the units are. So the first thing you must do always for any equilibrium problem is write a balanced chemical equation. So here it is. And so then you've got to write the solubility product expression. So these are my products. They're both aqueous. So here they are in the numerator. Notice this is raised to the second power because the coefficient in front of the hydroxide is 2. The solubility product, it's not given in this problem, but you can look it up in a table. All right? So there's a table in your book, and if you're taking a quiz or exam, it's either given in the table right there or it's actually given in the problem itself. All right, because we're going to be converting remember the brackets here represent concentration of moles per liter. So we need the molar mass of the copper 2 hydroxide in order to convert this moles into grams, and that will have grams per liter. So we have to have this as a conversion factor for there. All right, so let's go on to the next slide. So you set up an ice table like we've been doing all this semester, or all the last 3 chapters. So here it is, my balanced chemical equation. Initially, I have 0 of the 2 ions. And then for every one of these that dissolves or dissociates, I get S amount of copper and I get 2S amount of the hydroxide because of that coefficient there. So let me just say this is the most common mistake I see students make is you take this and you put it into your solubility expression and then you square everything. You square this and then you multiply it by this. So 2 times 2 raised to the second power is 4. So don't multiply, it's 2 raised to the second power is 4. And then you have S squared, and then you're multiplying it by another S, that makes it S cubed. Just make sure you focus on this. This is where I see students make the mistake the most. All right? So then what you do is you divide both sides by 4, and you take the cube root. And so on your calculator, you have cube root, you can say x raised to the y power and then say 1 divided by 3. That's the cube root if you want to do it that way. And so when we do that, you should get 1.8 times 10 to the negative 7th. So you should do this on your calculator and see if you get this actual value, and that'll give you an indication if you're using the using your calculator correctly to solve for that. Okay, especially the cube part, because this can be to the 4th, it can be the 5th or 6th or something like that. So you got to learn how to input this correctly in your calculator. All right, so once we do that, we know that S stands for the amount of copper ion that uh, is produced. And since it's a 1-to-1 relationship between that and the copper 2 oxide or hydroxide, then we know how much copper 2 hydroxide was dissociated. Okay, so the amount of copper 2 hydroxide that dissociated or dissolved in water is this. But we got to convert the moles to grams using the molar mass of copper 2 hydroxide, which was calculated on the last page. And so we find out that the amount of copper 2 hydroxide that dissolves in water at 25 degrees Celsius is 1.7 times 10 to the negative fifth grams per liter. So this is solubility. Let's go back a slide. And let's go back a slide. And this number here is solubility product. They are different things. You solve for S, which is solubility. And when you solve for S, you didn't find solubility. You found molar solubility. The question asked for solubility, so that's why you have to know the molar mass for copper 2 hydroxide, or at least calculate it out. And that's what we used here to calculate that out. All right, let's have you do a problem. So it says the solubility of calcium sulfate is measured experimentally to be 0.67 grams per liter. Calculate the value of KSP. So this is the reverse. This, when they give you the solubility, and you have to reverse it back to how much calcium sulfate, what the solubility product of calcium sulfate is. So if this is in grams per liter, we need to get this into moles per liter to get the molar solubility. So how do you go from grams to moles? Use the molar mass of the substance. Okay. So the molar solubility of calcium sulfate is the 0.67, the solubility that we have here. And then we use the molar mass to convert the grams to moles, and we find out the solubility of the of the calcium sulfate is 4.9 times 10 to the negative 3 molar. All right, so the next thing you want to do is you want to write the equation for calcium sulfate dissolving in water. You have to have an equation in order to do solubility or any everything we've done. If we're dealing with equilibrium expressions, you have to have a balanced chemical equation. So here it is. All right. And then here's the solubility product expression. Products over reactants. Here's my products. The reactants is solid, so it's integrated into the solubility product. I know that the molar solubility is this, so I plug that in for this S, and I plug that in for this S, and if I square that, that gives me the solubility product for water. I mean for calcium sulfate, yeah, calcium sulfate. So that's how we've done the reverse here. Here we've taken the solubility, converted to molar solubility, plugged it into the expression, found out what the solubility product is. Says this is a relatively large KSP, so calcium sulfate dissolves. It's still not favored. Let's get real here. It mainly stays in this form, but 10 to the negative fifth is larger than 10 to the negative 30th. That's what they're saying here. Relatively large compared to other solubility product values. Okay. So how do you predict when a reaction is going to form a precipitate? Well, it's just like equilibrium. If Q is less than K, we know the reaction goes in a forward direction. If Q is greater than K, we know the reaction goes the opposite direction. So we're going to use reaction quotient to predict when a precipitate will form. Q has the same form as KSP except for concentrations of ions are not at equilibrium concentrations. Remember, Q is non-equilibrium concentrations. So we've done this. It's just doing what we already know and applying it to solubility versus acid-base reactions. All right, so first thing we're going to look at is, here we go. We're going to mix. So here's what we have. We know that silver chloride is a solid in water. It's insoluble. And it's in equilibrium with the silver ion and the chloride ion. So here's the equilibrium expression for or let's call it reaction quotient expression. So what this means is that these are initial concentrations. These are not equilibrium concentrations, and that's why we don't have a K here. We have a Q. So here's what we know. If Q is less than K, no precipitate will form. Because if Q is less than K, the reaction is going to go in a forward direction. That means more ions are formed and no precipitate will form. If Q is less than K, oops, this thing is wrong here. If Q is greater than K, there's a mistake there. Then a precipitate will form because the reaction goes this way, back to the reaction goes this way, back to the solid. All right, so maybe that's caused confusion. This is important. This is it right here, right? All right. So let's look at, if it's Q is great, let's not say equal. Let's see, we just want to say Q greater than K, yeah. All right, let's put it to work here. So we have a problem. I don't know if I'll do all of these. I mean, we can do some of them, but let's do one of them at least. So let's look at the first one. So predict whether the precipitate will form in when each of the following is added to 650 milliliters of 0.0080 molar potassium sulfate. All right, so here's what we got to know. First of all, we have to know the solubility product for barium sulfate at 25 degrees Celsius. So we looked at it in a table. Here it is. When we think about precipitation, we have barium sulfate. It's a solid, and then it's going to be in equilibrium with its two ions. Barium 2 positive plus sulfate 2 negative. And these are aqueous. I didn't quite give myself enough room for that. Aqueous. And you know that the solubility product for this is equal to the barium ion concentration times the sulfate ion concentration. And my bracket's a little off there. Now, we are not solving for KSP. We're solving for Q. KSP is already given. We know what that value is. It's this. So what we're solving for is the reaction quotient. What is the initial concentration of the barium ion? And what is the initial concentration of the sulfate ion? And if that Q is greater than KSP, then that means this reaction is going to go in this direction and we're going to form the precipitate. That's the way it works. Okay? So here's what we have to do. We have to take the volume here and we have to multiply it by the molarity. And that will determine, and then we look at this for every 1 mole of potassium sulfate, we have 1 mole of sulfate ion. So we can figure out what the concentration initially is of the sulfate ion. Or at least, let's do this, the number of moles. We're going to determine the number of moles of the sulfate ion initially. Now, the reason why I corrected that was when you go to make it a concentration, you've got to add the 650 milliliters to the 250 milliliters you have here for the total volume. So don't forget to do that. I find a lot of students make that mistake. So 250 and 650 means we're dealing with 900 milliliters of solution. And make sure you label this stuff. 900 milliliters of solution. And then how we know what the concentration of the barium ion is, we're not interested in the chloride ion because it's a spectator ion. We're going to multiply 250 times 0.004. That's going to give us, actually, this gives us millimoles. All right, let me just say that again up here. So that gives us millimoles of barium ion. And then we're going to divide by the 900 milliliters of total of solution. And we'll know what the concentration of the barium ion is. We'll plug those into our reaction quotient expression. And if Q is greater than K, then we know the reaction is going to precipitate. So let's look at that. So here's what they did. They took the milliliters of barium solution, they multiplied that by its concentration, and remember we're talking about barium chloride here. So it's a 1-to-1 relationship between barium ions and barium chloride concentration. So there it is. 250 milliliters of barium chloride gives me 250 milliliters of barium ion. And that's why they're writing barium ion in brackets here. Divided by the total volume of the solution now. Because you combine the two solutions together. This is one of the most missed parts of the problem right here. And that will give you the molarity, the molar solubility of the barium ion. Do the same thing for the sulfate. Take the volume of sulfate, and it's a 1-to-1 relationship between potassium sulfate and sulfate. So we multiply these, we get the moles of the sulfate ion, and we divide again by the total new volume, which is 900 milliliters, and we get this molar solubility for actually, I just want to say, I don't know if I want to call it molar solubility. I just want to say it's the solubility, it's the concentration of the sulfate ion in solution. I guess that's a better way to say that. We take these concentrations and we plug them into our reaction quotient expression. We get this number. That number is larger than the solubility product. If Q is greater than K, the reaction goes in this direction, and that direction is the solid barium sulfate versus the barium ion and the sulfate ion over here. All right, and so barium sulfate will precipitate. All right, let's do one more. Let's make sure we understand what we're doing here. So let's go back a couple of slides. All right, so we have silver sulfate, okay? They got a typo here, so let's fix that. This is a subscript 2. Here's the solubility product of silver sulfate. Okay? So maybe you want to stop the video at this point, try this out on your own, and then see if yours matches mine. If it does, that means you understand it. If it doesn't, that means you need more practice. Okay, so you may want to stop here. All right. So before we get started, let's go back because I want to point out something here. You have 175 milliliters of 0.15 molar sodium nitrate, 650 milliliters of 0.0080 molar potassium sulfate. So look at this. This is where we're going to use this to determine the number of moles of silver ion in the solution. And we're going to use this to determine the number of moles of sulfate, which you've already done. So that's going to be redundant. The only thing that's going to be different is the concentration is going to be different because we're not using 250 milliliters of solution like we did in A. We're only using 175 milliliters of solution. So it is going to be different as far as concentration goes. All right. So 175 milliliters of 0.15 molar silver nitrate. Now again, silver nitrate, it's a 1-to-1 relationship. For every 0.15 molar silver nitrate solution, I have 0.15 molar silver ion. So make sure you do that. Make sure you check your work and make sure this is 1-to-1. This is 1-to-1 with the silver ion. Because if there had been a 2 here, then you'd multiply that by 2, right? For every one of these, you got 2 silvers. That's not happening here. It's 1-to-1. And then the total volume is the 650 milliliters of potassium sulfate we added, plus the 175 milliliters of silver nitrate. So here's my concentration of the silver ion. The sulfate ion we've already done. It's 650 times its concentration divided by our new concentration. It's not the same as the other one because there's only 175 of the silver nitrate. But this is the concentration of the sulfate ion in the solution. Again, what are we doing here? We're going silver sulfate solid dissolves into silver ions, 2 silver ions. All right, let's make this correct. And 1 sulfate ion. And again, these are AQ. Again, I missed it. All right. So that's why the expression looks like that. Notice the 2 here to represent the coefficient of 2 here. So we plug in the values that we have for the silver ion concentration. We plug in the value we have for the sulfate ion concentration. Don't forget to square this one because it's a 2 here. And then multiply by that and we get this number here. And then we compare that to the actual solubility product. And this number, 6.5 times 10 to the negative 6, is less than 1.5 times 10 to the negative 5th. So Q is less than K. And we know if Q is less than K, the reaction goes in the forward direction. So silver sulfate will not precipitate. Will not precipitate. All right. I think these are fairly easy. You know, they're not as complicated because we don't have a denominator, right? The denominator is the solid, and it goes over into the constant itself. And really, what it's playing on is Q more than anything. If Q is greater than K, the reaction goes in reverse, and the precipitates form. If Q is less than K, the reaction goes forward. Just like we've learned that over and over in the previous chapters. So I think this should seem fairly easy compared to, because we've done all this other work. So I hope it is. I hope it works out for you. I'm not going to do the last one. I'll let you work on that. All right, I'm going to stop here. I think I'll break it down into 2 topics. We're at 38 minutes. I think we'll stop here, and then I'll do another video to finish out Chapter 17.